Welcome back everyone. In this lecture, we will actually see some universal constructions of some important modules. So, namely tensor products, symmetric products, exterior products and so on. So, let me actually recall briefly about all these objects. Okay, I am going to actually kind of give a very quick introduction to all these universal objects. So, mostly these things must be covered in the first course of algebra, but anyway let us see, because these constructions give us many important examples. So, we need to be very comfortable with them. So, let us start with the construction of tensor algebra. So, which is in some sense very important for all other objects. So, let us start with the vector space. Let us take V being, so we can just assume to be finite dimensional vector space, there is no issue. So, let us take V be a finite dimensional vector space. Let us work over complex numbers as always. So, then we can also fix a basis for this V. So, let us take the basis to be V1 etc. Vn. So, where n is the dimension of the space. So, now we have already seen actually the construction of tensor products. Okay. So, given any k which is non-negative integer, one can actually take this kth tensor product. So, that is V tensor V k times. So, basically this is the kth tensors. So, we have very natural basis for this tensor product. Okay. So, once we fix the basis V 1 etc. V n of capital V, then it is not that hard to see. We have this standard basis V I 1 tensor etc. V I k, where I 1 etc. I k that actually comes from this 1 to n. So, where I 1 etc. I k, it just comes from this 1 to n. So, this will form a basis for this t power k v. Okay. So, this is just a general fact. So, now once we have this k tensors, okay, these are called k tensors. So, now given 2 of these k tensor and k dash tensor, we have a natural bilinear map from t k of v cross t k dash v to t k plus k dash v. Okay. So, let us define that. So, we have t k v cross let us say t k dash v to we have t k plus k dash of v. So, what is this natural bilinear map? So, this is given by, so this is simply a writing one tensor next to each other. So, this is the juxtaposition product. So, you take V 1, okay, let us call it W 1 tensor etc. W k, and then we take some U 1 tensor etc. U k dash. So, it is enough to define it on the simple tensor products, and then one can linearly extend it to the space. Okay. So, then this is mapped to W 1 tensor etc. W k tensor U 1 tensor etc. U k dash. So, there is this bilinear map. Okay. This is indeed a C bilinear map. So, that is defined between these spaces. Now, this bilinear map actually can be linearly extended to T of V. So, that is what gives us product on T of V. So, we can extend this map linearly, of course, linearly in each variable to all of T of V. So, in particularly we get a map from T of V to T of V cross T of V to T of V. So, this is the product that is defined on T of V. So, T of V becomes C algebra, indeed associative algebra with respect to this product. So, this way we can make T of V as C associative algebra. Okay. So, which is called tensor algebra. So, this is not just merely a vector space, it has this product structure, and that product structure makes it it is a C algebra, and that algebra is called the tensor algebra associated this way. So, now we can easily see that the product that we have defined is naturally a graded product. So, that makes actually this T of V indeed graded algebra. So, this is indeed graded C algebra. So, what is the meaning of that? That means if I take some element from Tk of V, and then if I take some other element from Tk dash of V, if we take the product of that, then that should lie inside Tk plus K dash of V. So, that is how we have defined the product. So, that means it is graded algebra. So, note that T of V, which is the tensor algebra, okay, by definition it is the direct sum of all of Tk of V. Okay, this is the direct sum of Tk of V, where k ranging from 0 to infinity. So, yeah, this should have been defined in the beginning itself, but anyway, okay. So, we have this T of V, which is the direct sum of Tk of V, on which we have defined this multiplication, and it is naturally a vector space. So, that makes this as a C associative algebra. So, now let us actually have a closer look at this algebra. Okay. So, one can define something called free associative algebra generated by the variables V1 etc. Vn. Okay. So, let us call this as C angle bracket V1 etc. Vn. So, what is this? This is free associative C algebra generated by the variables V1 etc. Vn. Okay. So, there is this universal construction, one can do this. Okay. So, if you do not know the definition, maybe you should go back and then just check the definition of this. So, then it is easy to prove that T of V as an C algebra is naturally isomorphic to this free associative algebra, okay, as a C algebra. Indeed, this actually gives us how one can think about the elements of T of V in terms of the monomials in V1 etc. Vn. So, if you think about it, basically the simple tensor Vi1 tensor etc. Vik. So, this corresponds to the monomial Vi1 etc. Vik. Note that it is a free associative algebra. There are no relations between the variables Vi. That means the variables Vi do not commute. Okay. So, the monomial, this ordered product matters us. Okay. So, this is indeed ordered product. So, in which we write the order matters. So, the variables Vi's do not commute. Okay. And then you can take all possible monomials that can be formed from these variables V1 etc. Vn, and then take C span of that. So, that is going to be your free associative algebra. So, where the product is given by just writing one monomial next to another monomial. So, that is the product so that gives you C algebra structure here, and then with that algebra structure you can see that T of V is isomorphic to this free associative algebra generated by V1 etc. Vn. So, these are all some general facts. Okay. So, one must know already. Okay. So, now if we start with the G module, then what happens? Okay, then it is easy to see that T of V becomes naturally a G module again. So, if V is a G module, then it is easy to see that we can define G module structure on the K tensor, okay, is also a G module. So, how the G action is defined on the kth tensor, it is again by derivation. So, if I take x and then if we take some k tensor, again it is enough to define it on the simple tensors, and then you can just generalize, then you can extend linearly to all the elements of this Tk of V, because it is spanned by the simple tensors. So, if you take some simple tensor W1 tensor etc. Wk, x acting on that by derivation, what does it mean? So, it means x first act on the first coordinate, and then you have all the remaining coordinate as it is, then it acts on the second coordinate, then all other coordinates stay as it is, and so on. Then finally, it acts on the last coordinate. Okay. So, this is just by acting by derivation rule. So, that makes Tk of V as a G module. So, that means Tv, because the direct sum of Tk of V. So, this is also a G module, also a G. Okay. So, we have many interesting representations coming from this T of V. Okay. So, what is about other constructions? So, let us now look at what is called symmetric algebra and symmetric tensors. Okay. So, let us look at symmetric algebra, which is easy to define from algebra point of view, and then we can relate that with symmetric tensors. So, once we understand this very clearly, then it will be easier to understand the exterior algebra and exterior tensors or alternating tensors. So, what is symmetric algebra? So, symmetric algebra, it can be defined easily from the tensor algebra. Okay. So, you can take this two-sided ideal generated by these elements. Okay, let us call it as the ideal I. So, this is the two-sided ideal, generated by the elements V tensor W minus W tensor V. So, where V and W varies over capital V. Okay. So, what we want to say, whenever we flip two tensors, we want to say that so there is no change. So, V tensor W should be equal to W tensor V. The way we want to actually do that, so algebraically just take the two-sided ideal generated by that, go modulo that. So, then you get the necessary algebra that you are interested in. So, you take T of V modulo I. So, that is what called symmetric algebra. So, purely from algebra point of view, what we are doing. So, tensor algebra gives us this free associative algebra generated by the variables V1 etc. Vn, where V1 etc. Vn do not have any relations between them. That means, whenever you consider the monomial Vi1 etc. Vik, the order in which that is written matters for us. But if you take the symmetric algebra, so we want to demand that the variables Vi commute. Okay. So, that means we go modulo this two-sided ideal generated by V tensor W minus W tensor V. Then what we get is indeed C algebra, which is associative plus commutative. C algebra, again generated by the variables V1 etc. Vn. Okay. So, there is this natural map from T of V to S of V, okay, which is actually, let us say, the image of the simple tensor vi1 etc. vik is mapped to just vi1 times etc. vik. So, now the variables vi commutes. So, that means one can actually arrange this in the increasing order or the decreasing order. So, we can simply arrange it as just I1 etc. less than or equal to etc. ik. Okay. So, that is what we can do here in the symmetric algebra. So, we can arrange So, that means you can see that this ideal that we are going modulo to get the symmetric algebra is indeed graded ideal, because it is generated by degree 2 graded elements. So, these are degree 2 graded elements. So, because of that we get what is called graded ideal, we get a graded ideal. So, because we are going modulo graded ideal, the algebra that we get again it becomes graded algebra. So, this is again graded algebra. So, what will be the graded component? So, you take the grading on T of V, just surject on S of V, then whatever you get there will be the grading for the S of V. So, that means all we do, we can take this Sk of V. So, which is just a suggestion, let us call this map quotient map pi, then you take pi of Tk of V. So, that is your Sk of V. Okay. So, by definition it is indeed the kth symmetrized tensors. So, we will actually naturally identify this Sk of V as a subspace of Tk of V, okay, but so that is just as a vector space one can identify. So, okay, let us actually look at what can be the basis of this Sk of V. So, you can easily see that we have this natural basis for Tk of V. So, which is given by all the words vi1 etc. vik, where I1 etc. ik just varies from 1 to n. So, which has length k. Okay. So, then if we take that basis and then take the image of that, that is going to be basis that is going to be a spanning set inside your Sk of V. Okay. So, definitely it is spanned by vi1 etc. vik. Okay. We can take all I1 etc. ik coming from 1 to n. But the thing is, since the variables actually commute inside S of V, so we can arrange them in the increasing order. So, that is actually allowed. So, that means we can just simply arrange them. So, then one can prove that this natural set will be form a basis. So, this will be a basis for Sk of V. Okay. So, because of this universal constructions, one can just take the natural set that it descends to, then that will be actually basis for this Sk of V. So, now it is not very hard to actually compute the dimension using this observation. So, the dimension of Sk of V, if you think about it, you are indeed forming a monomial of degree k with the variables n variables v1 etc. vk. So, this means this is exactly the number of monomials that we form, okay, monomials of degree k that formed from the variables v1 etc. vn. So, of course, when we say monomials, it is a commuting monomials. Okay. So, that means this is exactly, if you think about it, is the coefficient of this multinomial coefficient. So, this is exactly n plus k minus 1 choose k. Okay. So, I will leave it to you to check this, that this form a basis and the dimension of this is exactly n plus k minus 1 choose k. Indeed, so we have this natural multiplication on S of V coming from T of V, because we have gone modulo the two-sided ideal generated by these elements. Okay. So, that means there is a natural C algebra structure on S of V, because we have gone modulo the graded ideal. So, we are going to get a graded algebra. So, if you think about it, S of V is indeed direct sum of this Sk of V, where k range from 0 to infinity. So, this is going to be naturally isomorphic to the polynomial algebra generated by V1 etc. Vn. Okay. So, that is because these variables V1 etc. Vn commutes, and this is the free, okay, this is a free associative plus commutative C algebra generated by V1 etc. Vn. So, that means it has to be isomorphic to this S of V. So, this is just from the algebra point of view. Now, what is about the module theory connection? Okay. As representations, we have some relationship between symmetric tensors and this Sk of V. So, let us try to actually understand that. So, if we start with V being G module, suppose V is a G module. So, then that implies this T of V is a G module. Now, if you think about it, it is easy to see that the ideal I that we have taken, that is a G invariant ideal. So, I is a G invariant ideal. So, that implies that when you go modulo that ideal, again you get G module. So, which is S of V. Okay. So, for example, how one can actually verify that it is G invariant, because this is two-sided ideal generated by these elements. Okay. This is two-sided ideal generated by V tensor W minus W tensor V, where V and W coming from capital V. So, it is enough to actually say that when you act via element of x in G, then these generators actually somewhat leaves invariant. Okay. So, let us look at what happens. So, let us act by x on this generator x V tensor W minus W tensor V. Then what we get exactly? We get x V tensor W plus V tensor x W minus x W tensor V minus W tensor x V. So, if we think about it, we can actually group these two elements x V tensor W and minus W tensor x V, and then we can group these two elements. So, that gives us that x V tensor W minus W tensor x V. So, which is in the generating set, plus V tensor x W minus x W tensor V, which is also in the generating set. So, that means this is again in the ideal capital I. So, that means I is G invariant. So, once you know that I is G invariant, once you go modulo that ideal, then again you will get G module structure on this quotient. Okay. So, that makes this S of V as a G module, and it is not difficult to prove that if you take some length k element, which is V I 1 etc. V I k from Sk of V, then and for any x in G, it is easy to prove that x acting on this V I 1 etc. V I k is again element of Sk of V, because the natural action is just the derivation action. Then you can see that x dot V I 1 etc. V I k is going to be just summation V I 1 etc. x some V I r times etc. V I k, where r is running from 1 to k. So, which is again of the form k product. Okay. So, this is has to be inside Sk of V. So, that means each graded component is again SKV module. Okay. Sorry, each component SKV is again a G module. It's a submodule. Okay. So, now let us actually look at the relation between this Sk of V and the simple and the symmetric tensors. So, what are the symmetric tensors? So, basically the symmetric tensors, okay. So, by definition, so they are the tensors, simple tensors, okay, spanned by the simple tensors that are actually invariant under the action of the symmetric group Sk. So, let us actually make it very precise. Okay. So, let us take this k tensors Tk of V, which is just a tensor product of k copies of V. So, now the symmetric group Sk acts on Tk of V. Okay. So, by permuting just the tensor components. So, if you take sigma and then if I take some Vi1 etc. Vik, so then simply you apply sigma on the indices. Okay. So, maybe we will use W1 etc. Wk, because we want to just permute the indices. So, then the sigma, it is just going to just permute those corresponding tensor components. So, then it gives exactly W sigma 1 etc. W sigma of k. So, this is again element in Tk of V, and this induces actually action on Tk of V. So, now once you have the action of the group, then we can talk about fixed point elements. Okay. If I take this symmetric K of V, by definition, this is those vectors inside K of V such that they are invariant under the action of this Sk. That means, when you apply sigma, that the W becomes invariant. So, sigma W becomes W for all sigma in Sk. Okay. So, this is indeed the set that we are interested in. So, that is the symmetric tensor actually. So, this is called symmetric K tensors. So, now one can easily verify that the action of G indeed commutes with the action of Sk. Okay. Suppose V is a G module. So, then the action of G commutes with the action of Sk. So, in particularly on Tk of V, in particularly that implies that the symmetric power becomes a G module. Okay. So, we have again module structure on this sim K of V. So, we have a natural map from Tv to Sv, and then if we restrict this map to actually this sim K of V. So, we restrict this map, let us call it pi. So, pi you are restricting to sim K of V. So, this is going to map sim K of V to exactly the Sk of V. Okay. So, this is a natural map that we have. What one can prove? That one can prove that this is indeed vector space isomorphism, and if we actually take V being a G module, then this is indeed G module isomorphism. So, all important thing is it is an isomorphism of vector spaces. Okay. This is an isomorphism. Okay. So, indeed the inverse map is actually very well known map, which is called symmetrization. So, what is symmetrization? So, the symmetrization is, if I take element inside this Sk of V, let us call it some Vy1 etc. Vik. So, it is written in some order, okay, because the order does not matter. Then what we can do, we can actually associate this natural element 1 divided by k factorial sigma inside Sk, where you can apply sigma on all these elements. So, you can just simply take V sigma 1, okay, maybe we can just do it on the any k tensors W1 etc. Wk. If I take, then we just simply apply it on W sigma 1 tensor etc., tensor W sigma k. Okay. So, this is indeed a map from Sk of V to sim k of V. So, that is actually easy to see. Okay. So, you have a natural map which is the inverse map of this restriction map. Okay. So, I will leave it actually to you to check this is indeed gives you isomorphism. Okay. So, in particularly you can see that there is a natural basis that is actually coming from the basis of Sk of V. So, which looks like the you can take the basis here in the Sk of V, use this symmetrization map, and whatever images that you are getting in the symmetric tensor, that will be a basis for the sim k of V. So, this way one can actually get many interesting representations. Okay. Sometimes it is easy to actually think the elements of sim k of V as just words. Okay. So, the words that just commutes in the variables that actually comes from the basis of capital V. Okay. Or otherwise one can also think them as elements inside the tensor product, and then you can actually just symmetrize it, and then you can actually take elements from the sim k of V. So, both has some advantages. Okay. So, the important thing is all this sim k of V, they are G representations for any given G module. Okay. So, I will stop here, and then we will continue with the construction of alternating products in the next class. Thank you.